Agree.
Does that look right?
But you have to.
That's hard.
Congratulations. Join this with this.
Oh,
معلمه عربي
هو جابها
Yes.
تخريج كده برضه. ماشي 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 تخريج.
Join like this.
straight or
Straight, yeah. Yes.
تخريج.
Yeah. Congratulations.
all right. There we go. I can use my translate app. No, this one was Apple.
Well, good morning again. Probably this is our last good morning because tomorrow we will have a good afternoon. So today is our last good morning and day number 10 of this workshop. I hope you had a good time. And from the team, we were more than happy to share everything we know. So today is sort of wrap-up day. We are going to show you or present to you, between Burdette and myself, some concepts that complement or are connected to the topics that we show you during the last days. So we are going to make a additional emphasis on the remote sensing part in order to introduce you to these topics. And these topics might be already areas where you're working or doing research, or you have learned, or you see opportunities of research and collaboration there. So having said that, let's begin. How much have we progressed on remote sensing? We have two sources now of information, satellites and drones. And from the satellite part, we have progressed a lot. When I was studying remote sensing with Christopher Neal, we had to download what we call it the raw data or level 0, that as we mentioned it in the workshop. Do all these corrections and tweaks to the data to reach level 2, which is the level that now NASA provides us directly. All of that science now is part of an automated process, and now we can focus mostly on deriving products based on that level 2 scientific data. That's good.
That's pretty new. So level 2 reflectance has been around for 7 years, maybe something like that.
Yeah.
But the surface temperature is much more recent than that. So
Yes. And initially was only for the US, but they expanded the scope for everywhere in the planet. So we can benefit from that. And Landsat is not the only source of information. We have Sentinel-2, which we haven't covered in this workshop. We have MODIS, which is used for, let's say, basing scale analysis and has the same amount of, or the same type of information than Landsat. So we can calculate evapotranspiration and other variables with MODIS data too. And we haven't touched that. There is more and more data that are more and more satellite. Now there are companies launching their own fleet of satellites, and one of them is Planet. And as you saw from the tiny presentation we made on that, and the note that I sent you through the WhatsApp, you can have access to that data. It's a matter of your application for that. So that's good. That's good because not all remote sensing data is the same. 30 meters might work for the new Delta, but not necessarily for the older or the fields that are, but these other sources of information like Planet might be viable, but you are the ones that have to evaluate that data and say, yes, this is good. We need more of this data. And NASA keeps preparing new, more advanced sensors. They're going to launch what is called a hyperspectral sensor in space. So instead of having how many bands we have from band 1 to 7 and then band 10 for thermal, they're going to launch a sensor that has 255 bands that goes from the coastal blue, from the 400s all the way to the 2300 nanometers. The amount of data and the computational power required to process the data is absolutely different. It's going to require a higher level of magnitude than these computers. So one of the things that is happening these days is cloud computing. In this workshop, we work everybody on these computers and we're able to work with one image. If you're doing research, sure, you will work a second, a third, 10 images, 20 images individually. But what if we have to target the entire Egypt country? What if we have to target 5 or 10 years worth of analysis? That implies that we have to level up our skills towards programming, towards the use of cloud computing. And in the remote sensing presentation, we left you a lot of information about Google Earth Engine, which is one of these platforms that is for free, that you can do remote sensing. The price to pay to use that platform is Python. Learning to program in Python. And it's not that hard. Okay, another thing that I wanted to mention here is there are companies that are coming that are offering interesting types of products. Planet offered optical and near-infrared data. Hydrosat, on the other half, it's offering thermal data. Hydrosat is offering this. Actually, Hydrosat has bought or is buying Earwatch. This is becoming the next power horse on commercial remote sensing products in the commercial satellite environment. So this is progressing, and we need to keep track of this. How do we keep track of this? Well, for once, I subscribe to the to NASA RSET, which I mentioned to you on the second day, I think. Subscribe there, learn what NASA scientists and collaborators are doing and how they're using the data. You might find really good applications there. The second thing is I follow NASA in Twitter. And I follow the US Geological Survey because they manage Landsat. And I follow Planet. And as I learn from these companies, I try to follow them in Twitter. And this is my source of news of what's happening in the remote sensing realm. On the side of drones, you were able to participate in a field data collection day. Then you took that data already processed and you apply the same algorithm we use for satellites, we use it on drones. We had to define certain criteria to evaluate that data. We couldn't use it at the original resolution. We had to do some resampling because of the variable, which is the Leaf Area Index. That was our course's source of information. But they're improving really fast. The multispectral data is level 2 data. It's really good. But the thermal is still at level 1. Level 1 means you need one more additional correction, and then you get level 2, L2 thermal data. So that's great. This is evolving as the sensors become more powerful. We incorporate computational capabilities to those sensors and to the drones. We will see that the cost of this technology will start going down, becoming more attractive for agriculture in general. Right now, it's still pricey, and the algorithms requires science. So we need to make the algorithm reliable, so a person with a basic training can just run. The proximal sensors, and some of you have mentioned that are working with proximal sensors that are closer to the objects or to the surfaces without contact. This is also evolving really fast, and we're seeing now an emergence of robots, ground robots for agriculture. And these robots are carrying sensors, and they are in this realm between robotics and the Internet of Things. These robots can have small thermal sensors, small cameras, have computational capabilities, they have GPS, they are collecting this data to detect early infestation of diseases, or lack of nutrients, or soil moisture, or amount of flowering, or fruit formation and quality. So this is evolving also very fast. And this, how we see is that all of these platforms will complement each other. And we're seeing some initial papers that are combining these two, and some initial papers that are combining these two. I haven't seen yet a paper that combines all the three, but that's what will happen. The farming of the future will not only have satellite, will have drones, but also will have ground robots collecting data.
Yeah, I'll just add, there's another big area in the proximal sensing is irrigation automation. So, and there's some pretty well established systems where they, mostly for center pivots, but they'll use proximal sensing and completely automate the irrigation process.
So, and all of this is remote sensing. Remote sensing, what is the meaning of remote sensing? Is obtention of information without contact. So all these sensors are based on the theory of light. They will use optical or thermal and variations of that to get data. Pictures, satellites. The future is going to be more bands every time, more bands, exotic bands like yellow bands, orange, multiple coastal blues, multiple shortwave infrared. Drones that will become more autonomous. In the US, there are companies already that are launching these drones.
Oh yeah.
And
There was military jets flying over. We could have gone out and watched them. They are celebrating 100 years of being able to refuel in the air. Well, that's a military flyover.
These drones are becoming smarter. They can fly now without supervision for 50 miles. That is about 80 kilometers from the pilot away. These are being used for example, railroad, train tracks monitoring, or power lines monitoring. So that technology will start coming to agriculture. And for us, what does it mean for us? This technology, if those drones that can fly 3-4 hours, what does it mean for us? Well, it means a lot of trouble. Why? Calibration. The optical sensors can self-calibrate, but not the thermal. So, do we need to have to put 10 thermal control points across the area if we need to fly 4 hours of these drones? That's impossible. We need to figure out a clever way to calibrate the thermal if we are going to use those drones that can fly for 2, 3 to 4 hours. So that's a challenge for us, for that technology coming. And sensors. This is becoming, as in the sensor demo, you saw the Atmos 41. Everything was compacted in this tiny unit that you can put in your backpack, put it on a pole, and you can start collecting data.
Scientific data.
Yes. So it's not anymore like that heavy duty weather station we saw on in the morning of the first day, that requires a large space and multiple supports and such. Now has become very common. And that's taking advantage of this miniaturization of the technology, improvements in Arduino and Raspberry Pi technology, low power consumption of sensors. And more of these ideas or more of these advances will continue happening. So the soil water balance, most of you understand this. You can draw this graph with your eyes closed, right?
Ooh.
That
Does
would
someone
be-
want to come draw this with their eyes closed? Huh?
We know this equation forwards and backwards. We have deal with a lot of time with this. So from the rest of the presentation, we'll try to cover these 5 points from the remote sensing perspective. We have target ET on this workshop, and I think you have learned a good deal about it. What about precipitation? What about soil moisture and the other components? Can we measure them with remote sensing? Now, this presentation is based on our experience and learning, but there might be groups somewhere that might be doing something that wasn't included here. And for that, we always try to keep our eyes open, but this is our personal take on how these components can be addressed by remote sensing.
We only know what we know.
Yes. We only know that we don't know everything.
Yeah.
Okay. ET, we show you OpenET. Remember that platform, you can go and click, and Catherine was showing us, okay, this is the ET for rice, this is the ET for soybeans, and we could see the trends and the patterns, the historical data. So it's very mature. We are at a point in history where the models can be used with confidence. We always need a bit of validation, but overall, the algorithms are extremely mature. They have been tested hundreds of times around the globe, so they work.
And they're more automated than in the past. So
Yes.
that's a big thing. It used to be, if you wanted to get ET with remote sensing for some study, you would hire a PhD student, and then all they would do is process imagery and run the models, and there was a lot of manual steps. And the models have come a long way in automating each of these processes. However, where we're short still is, for example, OpenET is only the western half of the United States. There are other groups, maybe less, I don't know, sophisticated than OpenET, that have ET products for other parts of the world, but usually using just one model. The value of OpenET is that they're using several models and trying to build off of the strengths of each model.
And OpenET was built in that way. So this validation process that we mentioned can allow us to define which of that 6 models that are implemented there fits better the area that we're working on or interested on. So, for example, in class, I used to tell CBAL is designed or will work better for areas that have a lot of rain. Like tropical areas will work really well, or let's say the east part of the US is better fitted for CBAL, while metric is better fitted for arid areas. So, but OpenET, but that was my 2 points of comparison. OpenET allows me to actually compare numerically all these different models behave in a specific area in the US. Their goal is to cover the entire continental US. I'm not sure about Hawaii, but they will do the continental US. I'm not sure about Alaska.
Wow.
So, but
There's not a lot of irrigation in Alaska.
but that's the goal. But as a project, and as a project initially supported by NASA and Google's and NGOs, it has succeeded on the goal to provide this platform. But now the challenge for that is how to keep it defined, how to keep it refine the model, sustain it over time. So we're looking for a business model that can be attractive, not expensive, but support everything that they need to do. So they need to become a paid system. OpenET is going to be open for researchers like us, so we don't have to worry much about it, but is how they decide a farmer, ex-farmer in Nebraska or California is going to pay for access to the data. So that's something that OpenET has to figure out. IRRIWatch, though, they already figured out that. This is the company of Wim Bastiansen, and maybe you have heard his name. He is the father of CBAL, the ET model called CBAL. And he developed a company around that model. And now he's offering his data all over the world. At some point, I was contacted to find a person, a sales representative in Peru, IRRIWatch. So they are all over the planet. So it's one of the multiple companies that will not offer NDVI, they won't offer SAVI, they will offer ET, they will offer Express, they will offer tree health or fruit productivity index. So values that allow the producer to make decisions rather than guessing. Like with NDVI, we just know that it's healthy or not healthy, right? But more targeted products that allows it to take control over irrigation, over stress management of or production forecasts or of the field. In the area of drones, again, also this is maturing fast. And the model that we show you, the two-source energy balance model, is a favorite of us. There is a reason behind that. There is one, but it's not the only model. There is here the links. These are the Python version of this. This Python version is, you can call it from ArcGIS Pro, but requires that you interact with the model in Python. We run the TSEP plugin because it was developed for in Vue.js because it was developed for that platform. And but nevertheless, this one is the one that we use for research, this version, because it allows us to select the additional options that the model has. like the formulation of the path resistance of the water from the soil to the atmosphere, that allow us to change assumptions about, for example, the soil heat flux from having it a constant value to a dynamic value. So it gives us more flexibility in research, but we have to deal with this on item. Now, there is metric, and you might have heard of this model because Rick Allen used to go to Egypt quite often and present this model. And also there is a Python version of it that can be used to process drone data. It has different requirements though. For example, we need to calculate total albedo. An additional parameter is total albedo. We have to calculate that. Well,
Well, the big thing with both of these is they rely on comparisons of temperatures.
Mhm.
You have to have a range of ET conditions for either of these to work.
yes.
And so if you have a very uniform field, both are poor, except for there are people that have used artificial targets. I don't know. Have you seen what Troy Peters has done? They used, I think, ceramic targets to try to force those conditions to exist for metric and not for Seaball. But these are similar models. Seaball came first, then metric built off of it. But the concepts are all very similar. You need to find an area, a pixel or group of pixels that are cool, vegetation that's cool, so it's transpiring a lot, and then some that are hot, and so there's very little transpiration or evaporation. And then there's a difference in how the two models, the rates they assign to each other. But that's something that's most easily done with satellites, possible with drones,
but
but you have to take care
of these extreme conditions that the model needs for calibration.
But they don't work for proximal sensing. Maybe for small image proximal sensing, but I'm not aware of a really practical scenario where these models would work for proximal sensing. The value of the two source model is that it has performed well under a range of conditions, and each pixel is its own. You might run the model for one pixel, and you could do it for just that single pixel. These two require a range of values. So that's, but because this one is each pixel on its own, it requires highly accurate surface temperature measurements. These two just need to have the differences between temperatures be accurate. And so the absolutes are taken care of within the model, which was a strength, especially before we had so many level 2 products available.
And I'm going to let you in a secret why my students are using TSEP. And this is the secret. Okay, I'll try to leave a smiling face. So TSEP gives me ET, right? But TSEP, the name is two source energy battles. The sources are plant and soil. What does it mean? Internally, I have E and I have D. I have internally the model calculate the contribution of evaporation and transpiration that summed give me the ET. This isolating T opens a very unique opportunity. The stress. Stress of the plant is calculated. There are different techniques. Pressure bomb, if you want to do it, like getting samples in the field, or with thermal sensors, looking at the difference between the temperature of the leaf of the plant and the air, multiplied with some conditions. And for every plant, there are different coefficients, and for every variety, there are different conditions. We hope that D will open the door to a general estimation of stress, because this one can be expressed like crop water stress index. It's equal to 1 minus transpiration over potential transpiration. This is our goal. We have studied ET a lot, and it works. And the opportunity that TSEP gives us to separate transpiration only opens the door to also calculate the level of stress of the plant without any assumptions regarding variety, regarding weather, regarding the stage. So this is our goal. So for us, our current job is to make sure that this partition is done correctly. So if we do this accurately, which currently we are not.
Yeah, so it's interesting with the two-source model is even though we compute E and T and combine to ET, we're better at this one than we are. There's more error in these two. When we add them together, we're quite accurate if we run the model correctly. And so even though we're getting them separately in the model, we're still not doing it as well as we would hope. But we're doing this pretty well. We should be able to anyway.
Yes. So our research work these days is in the separation. We already had a paper ready for publication that is showing that is in the right direction, but we need to refine this physical representation or numerical representation of the resistance or the movement of the water from the soil to the atmosphere. But we're close, and I expect in the next 1 or 2 years, this separation is going to be adequate so we can target that goal, because producers will want how much water you are using, but also if I'm managing fruit trees, nut trees, grapes, I need to know the level of stress my plant is to decide if it's time to irrigate or should I still leave it there. So
and there's a lot of crops where it's not that we don't want any stress. There's a specific stress window that we want.
And that's the jewel of the crown that we want to achieve. That's our prize.
Well, Alfonso, what is the difference between the crop water stress index and the depletion ratio?
Depletion ratio will be the changes in the soil moisture content due to transpiration, but it could be from fill capacity to a lower value or from any value to a lower value. Stress follows a specific path, I think. There is, if your depletion value goes from fill capacity to a smaller value, this is like a zone of no stress.
Yeah.
But if it's
Or
keep
minimal
going
stress,
down, the stress, there is a relationship between soil depletion and stress, but it depends also on the soil, the root, the root zone, stage of the plant.
So yes, and so if you think about like FAO 56, where the stress is all soil based. The difference is that this should be plant based. You can relate it to the stress coefficient that we use when we use crop coefficients, if you're familiar with that method. But those are soil based, where the value of this is we can go directly to the plant, but remote sensing, so indirectly, but we're not assuming that the plant behaves in a certain way based on soil water status. We're looking directly at the plant.
Okay. Finally, we shouldn't ignore there is a lot of science behind this basic concept that the NDVI and water use are related. This is going to be unique for the type of crop. Like alfalfa will have a unique relationship with the NDVI to estimate it. Almonds, cotton, each of them will have their own, let's say, equation. And this is something that the state of California implemented for the entire state. They decided at some point, how many years? Probably 10 years, more than 10 years ago, they found enough evidence that this was possible for the crops in California. So they did a large series of studies looking for equation for every crop they grow in there. So they have their own internal system where every farm, they can track the water use of every farm by knowing the type of crop on that plot. So I presented to you this equation. There is a very general equation, but for every California, the state of California and the site of California develop unique equations per crop. And this is something that is like a low-hanging fruit, because if there is a lysimeter, or if there is an eddy covariance, this one is quite direct, or having multiple years of the same crop and frequent values of NDVI, that equation can be rapidly be generated. So we don't discard this one. It works well, especially for crops that cover the entire of the surface, like corn, potatoes, soybeans, alfalfa.
Well-watered annual crops.
Yes.
Those are, it does not work well for natural vegetation. And tree crops are,
because of the dual environment, the interrow, which could be bare soil or grass, and the tree. That where there is weakness in this approach. We show you this, and you have access to it, right? So, as you have access, play with it. You can ask us question, where could I find a field of rice in this map? And Catherine already have coordinates for you. Or where is
does she?
Yeah, she took, so we can, and this is the Great Salt Lake, this is Bear Lake, we're just there. So
what might be interesting for some of you, just for comparison, is if we get down in this part of California, so very south and east in California, very south and west in Arizona. That's the closest we have in the United States to temperatures that get like Egypt. It's less humid here than in parts of Egypt, but not less humid than other parts of Egypt, right? So this is the closest you're going to get to temperatures that get up in that neighborhood of 60 C. So,
and drones. As the drones become more powerful with larger capabilities, we will be able not to map one field, multiple fields. And all of this area is almonds. This is 2 years all almonds, 5 years for almonds, 4 years, 8 years of all almonds. So we can see the variation of ET within the field. We can see that these all almonds, this value, the almond, the mature almond, 8 years old almond and older, use same amount of water as alfalfa. It's equal to ETO. So but these maps allow us, or these drone technology allow us to get the evapotranspiration at tree level. So this is something that is interesting for the producers, because they do trials. They run trials on certain lines or sections in the tree. They want to compare varieties. They self-pollinizing versus male, female varieties, and see how much water they use, or are they do they have more or less requirements of nutrients. So farmers are very proactive on that regard, because they're always looking for that extra productivity that can increase their income. As we did ET, we show it with you, and we had the opportunity to talk with Larry Hibbs. We don't want to forget that we need validation. Always, we need a way to confirm our numbers. Because let's say maybe we make a mistake on our thermal calibration, our ET comes up 2 or 3 millimeters higher. What does it mean? 2 or 3 is like 10 cubic meters per hectare higher. That's 1 millimeter of water. So that additional water, so any bias in my ET results will affect how much water that I put additionally or less. So we talked about the eddy covariance, and we heard from you that there are eddy covariance in Egypt now, and that might be a nice opportunity to kickstart a research on remote sensing ET. That's something for conversation. But also lysimeters. This is a 50-year-old concept that deals with water balance and can be used to validate ET. In fact, Metric was validated in Idaho over several lysimeters and to confirm the accuracy of that one.
And the lysimeter, so the best lysimeters are weighing lysimeters, but properly maintained water balance lysimeters, there's some that, so a lysimeter is a box, usually a still box, because that's more economical than anything else. It's a controlled volume in a box. So we have soil here and we have the plants growing out of it. Always at the bottom, there's some kind of gravel or something, a drain field, so that once the water has percolated through the soil, it can be removed by pumping or sometimes through a drain. But successful lysimeters have also been made smaller, that have an access tube through the middle that they can take something like neutron probe measurements, or you can outfit the box with soil moisture sensors. And you can make something like this for a lot less money than you can make one that is a weighing lysimeter. We have some old ones of these at one of our research farms, but they're all rusted out now. But no good. What's that?
This is a drain lysimeter.
Yeah, so this is a drainage lysimeter. But it's important to have some way on a drainage lysimeter to measure the water content of the soil. Otherwise, you can only get very long-term ET estimates. I've worked with the kind that doesn't have any way to get soil moisture in the middle in it. It's tricky.
Search now in Egypt,
Mhm.
there's 48 drain lysimeters. And we already installed the access tubes for time to manual reflectometer.
Okay,
To measure soil water content and determine soil water balance for some crops like tomato and potatoes
Mhm.
in this area. So it's cost effective than weighing lysimeter and less complicated, yes. But,
Oh, man.
weighing lysimeter is way more accurate. I
oh
think.
yeah, the weighing lysimeter is a well-maintained weighing lysimeter is like the best. It's the gold standard. I mean, we talk about how eddy covariance is gold standard, but the true gold standard is a very well designed and maintained weighing lysimeter, but that's very expensive. There are not many in the world that are done well. So usually only a few in each region of the world. But you could use this data, especially when you start to validate models over time, less concerned about an instance and more concerned about maybe a month or something. You could use that data and probably have a very good validation.
Validation for us is key. Now, for estimating spatial ET itself, biomass and a measurement of biomass, it's important. Some crops will allow us to use these septometers. There are new sensors that are coming that are LiDAR type that you can mount it on a tractor and drop around and collect LAI. Or the most basic one, the destructive method. Let's say you have a plot of soybeans, and every time the satellite will pass over, you look for a homogeneous patch in your field, take half a meter square of area, you harvest all the plant, and you measure the leaves. That's the destructive way. That's what
You scan them, scan these
one
leaves.
by one. Imagine scanning those corn leaves.
That's the good one to scan because they're like,
But Karen has to do that for turfgrass. For this tiny leaf, she had to put it, and it was a painstaking 2-day, 3-day effort to process the data. But that value is important.
I can talk to them if you want.
It's important also to know about the crop itself, because these are some of the inputs that diesel especially can benefit. The plant spacing or the distance between trees. For example, in vineyards, when we calculate maps of ET with drones, we calculate the pixel size is 11 feet or 3.6 meters. Why? Because the rows of the vineyards are separated in that amount. But when we go to trees, the trees are separated every 7 meters. So we calculate the ET pixels at 7 meters. So the resolution of the ET map is going to respond to how the vegetation is organized in the surface. But for alfalfa, for example, when we went over soybean, where everything is homogeneous, our consideration now is how we can measure LAI. What's the distance or the area that I need to get a reliable value of LAI? And that could be 1 meter, could be 2 meters, meter and a half. So depending how many repetitions could I do with my septometer and what's that area, that's my final resolution. So that separation. We don't do subplant ET, or to say alpha 3, because we cannot explain physically what's the LAI of alpha 3 or a quarter of a 3. I can explain the LAI of a 3, but not of a branch or just a tiny section of a 3. It's impossible to describe it physically. LAI, it describes the vegetation, the entire vegetation itself. So that's our criteria of how we use the characteristics of the plant to calculate the maps of ET.
We have to honor the physics of the models. And then on top of that, like Alfonso said, what does it mean if we know, oh, here's how much ET is happening here, this ET is less? You can't manage that. And so it doesn't, what's the value? All of our models assume that ET is only going up. And so we have to be modeling at a scale that's appropriate for this assumption.
Yeah. The other thing, and I've seen papers being published, but they are violating the fundamentals of it. Since they are doing ET at 5 centimeters, publishing papers. They present the tree or the crown of a tree, and they say, I got ET at 5 centimeters, and you see high values, low values all over the tree. What is happening at that tiny resolution, you get reflectors, but also you get shadows, you get glint. So you have noise in the data, that tiny resolution. So when we do this 2 meter, 1 meter pixel size, we are minimizing the noise, right? And approximating the reflectors, the true reflectors value of the solution. So if you see a paper that is saying we are able to do ET at sub-branch at a section of a tree, think about noise, think about the tiny shadows. Take a picture of like turfgrass, and you will see some leaves are not green, are shining. Other areas of the picture will be light, darker. So all of that is affecting the pixel value. So big that. Okay.
And at the leaf scale, this is what ET does. The vapor doesn't just go up, the vapor is going into the air mass around the leaf. We need to be at a scale, again, where we can assume that the vapor is going vertical.
And that's not at leaf 1 inch or 10 centimeters. It's much larger.
Also, if we could do it accurate, if we had, even for turf grass, if we had ET at this scale, we cannot manage it. You don't send somebody out with a water bottle and yeah, very precise, right? So another thing to consider is what scale can you manage to? So there's the minimum scale based on the science, but what if I have an alfalfa field and I could do 1 meter pixels in my alfalfa field, but then I'm running sprinklers on the field that are maybe 20 meters in diameter for how far they throw water. I can't manage 1 meter. I can manage about 20, right? And so that's another thing to consider is if I cannot manage that scale, why go to the effort of computing at that scale? Interesting for science, but for application, it's also important to think of what's the minimum scale. Maybe it's for water application, maybe it's for disease management. some of these things. So it's that all of those things are important to consider. Sometimes we get excited about, oh, we have the technology and we can get this so precise and so small, and it either doesn't mean anything or we just cannot manage at that scale, so it doesn't matter.
And that's where your criteria, engineers and scientists, need to come in. If I'm managing a very large center pivot that we saw in the new Delta, do I need drones or do I need satellite? If I have 30-meter ET, will that be enough to manage that center pivot, or do I need 1 meter ET maps?
I mean, it's better when we use a satellite. Better than use a drone.
It will be time effective,
Yes.
also cost effective.
Yeah.
But if you are managing, let's say, fruit trees, and you want to increase the quality of
One field. Yeah.
yeah, then information at tree level might be valuable and might be worth the cost of having a drone, a
Yeah.
camera, and personnel. So
Because we manage trees at the tree level. Usually,
so
people go out, they actually are pruning. When they harvest, even mechanically, they're still harvesting a single tree. We can manage a tree.
Yeah.
We don't manage an alfalfa plant.
I don't know, I have a doubt. Maybe in the long term, satellites will reach tree level. So maybe the
Yes.
advantage of drone will be only like avoiding clouds issues, or maybe like doing whenever we want it, because satellites, they have always the same time step, right?
Mhm.
So with drone, you can do it just when I want it or not.
and
That's
that's a really valid point. Drones are evolving, are trying to become this cost effective tool. But satellites are also saying, oh, we also want to be cost effective, and Planet is offering us 3-meter data. But if you pay Planet, they give you 1 meter data. And not a second fleet of satellites only for subscribers. Okay, and get 1 meter data on demand is what it means. You decide where you want your data. So 1 meter is getting pretty close to the drone. So the next iteration, in the next 2-3 years, is going to be 0.5 meter. And at that point, the two worlds collide, because 0.5 meter data can describe a thing. So as a satellite image can cover not 1 but 100 fields. So it will become more effective. So the tools we're developing while we're using drones, in the future, we won't care from where the data comes. We care about the science and the algorithms and the accuracy of these algorithms to be used. So
I understand from that selection between satellite image or drone will depend about the outcome we expect from our study. If it's small scale management, it's large scale management, and also, for example, for central pivots. In the case in Egypt, I'm not aware about the situation in New Delta. I have not personally been there yet, but in other central pivots that I have seen myself, they plant trees, they plant feeder crops in the central pivot, but around the central pivot to avoid wind issues, especially in desert areas and all that stuff. They start to plant citrus and some trees and install the irrigation in these areas. And sometimes they go further and do intercropping with some vegetables. If water is available in this area, so he is maximizing the benefit of his crop. So in that case, maybe drones would be more effective as in this scale to manage the field, central pivot, and also the trees and the vegetable crop between the trees.
it might.
Yeah, it could be.
Or it would be more, like you see, scattered information that we cannot manage on the smaller scale.
Mhm.
So drones in this case would be effective, or we still going with satellite image?
That's the question is, at what price you will sell those tomatoes.
Yeah, I guess that's a good
Because,
question.
because if the cost allows you to incorporate this internal technology, then it's good. But if your profit margin is tiny, satellite data is pretty like Landsat and others, so it just needs some processing, like the smaller cost versus drone cost. So the satellite is more affordable. So it depends. So it's always the selection of the technology, satellite, drone, or nothing, or like just recommendation from let's say the extension agency or the specialists, the agronomists, especially in the area, going to depend of how much can you afford based on your structure of cost and benefit to gain that additional profitability by investing that. So it's always it will end up being an economic question. So many farmers here in Utah don't use satellite. They use their vast expertise and the help of extension faculty from USU. And they get a good production, they sell their harvest to Japan and Middle East. So yes, but in California, these large companies invest on GIS labs with personnel and supercomputers and people that knows how to run TSET or AP models, and so they try to automate everything because that 1 or 2% increase or increasing yield or harvest makes millions for them. So it will end up being an economic question. To finish this slide, for drones, we need that extra work, the ground control points, and for now, the thermal control points. As technology evolves, these ground control points are getting away with the incorporation of RTK systems on board of drones. And thermal control points is still a pending question, but we believe it's solvable. So we will have these drones that can do everything by themselves and require less personnel in the field. And always, and this is important, your trustable agricultural weather station. We will always need climate data, air temperature, relative humidity, solar radiation, because this is what drives the remote sensing data to estimate the day eating.
Should we take a break now that we're changing
Sure. Let's take a break.
changing subjects a little bit?
Yeah. The coffee shop is open.
The coffee shop.
Do either of you guys have a science account?
I do.
Because in order to get money exchanged and avoid a $10 fee, they need to have somebody with it.
Okay.
Are you around this afternoon?
Yeah, I'm around today.
You still need those euros? This is the exchange rate here. And if you go with Dr. Debt, you can avoid the $10 transaction fee.
Yeah, when we're done today, we can if there's anyone that needs to go to Zion's, we can stop by the bank.
That's the one that's just on the north side of the road by that mall.
Okay.
Yeah, and they said the smallest denomination you can do is €5.
Okay.
Yeah, we used to have one on campus. There used to be a little one in the student center. That's why I have Zions. It's because when I was
Oh, yeah.
I did my undergraduate here
Yeah.
20 years ago, and
They're usually pretty good.
At
about
that point, I-
international stuff too.
they needed a Zions account.
Yeah, it was interesting. The last thing they told me was that it was Minnesota.
Yeah.
الاماونت الريت يعني كل دولار
Yeah, one
هو بص يعني انت لو معاك 5 يورو الدولار 5 او 10
David Rosenberg.
25.
Oh, willing to meet with her at 11:30 today. Yeah.
هو اعلى من الزيت هو في مصر كام؟
هو كده في مصر 26
مش عارف اديهم لك أنا لازم هدخل الاول مصر
It's not a very fun walkable line. It's kind of long highway, so. Yeah.
I only need a tiny bit of coffee for my rest of the day. I learned my
You've
lesson.
gotten very precise.
Yeah,
No.
I used to drink 5 cups per day.
Oh,
This is all that I drink per day now. Per
that's
day.
good.
That's all.
Very much.
No,
Schedule for tomorrow. You're gonna have a problem with tomorrow.
Yeah, I didn't, more than a month ago, I set up a workshop for tomorrow in Delta, so.
Will you be back by the?
No, I'm just gonna have to miss out on it.
quite funny.
Okay, so I can be around to help with the people with
Yeah.
the errands.
Okay,
I think Sheridan is also,
okay, that would be.
because he's in the field today, which means he won't be in the field tomorrow, so.
All right.
Yeah, so
Yeah,
Sheridan.
so between Sheridan, you and me, we can bring them.
Yeah, we just need to get them there about 3 o'clock. They'll have I can save you some food, I guess.
No, that's all right. No, I'm actually, since I'm gonna be down that way, I'm gonna be in Springdale later in the day, so.
It is a waste.
Okay. Yeah, I've got a
Okay,
couple day trip.
so I'll just keep track of you guys. then.
Yeah.
And then what?
Springdale, you ever been to Springdale? Have you ever been to Zion?
Yes, now I remember why I remember Spain.
Yeah, it's right at the mouth, it's the last community before the park. They have these small pastures and they're trying to figure out. Really, their problem isn't an irrigation problem. I think their problem is a pasture management problem. Uh-huh. Okay, so he's coming. He's gonna come after we're done talking, Dave.
No.
Oh, not today?
Yeah, tomorrow.
Okay, well, you'll see him tomorrow then. So-
It's Tuesday.
Yeah. Well, so he wrote this on the 23rd and we were gonna have him come here after we were done and he was gonna just give some final words. But since we're gonna go down to the water lab where his office is, he's gonna give some final words tomorrow. You'll have a chance to meet with him tomorrow for sure. Yeah. So, yeah, thanks. Now we have a few, Maha is meeting with Yumi. I think Samar is meeting with Pin. This is a good test to remember who's meeting with everybody. Adir's meeting with Dave.
The one that contacted Larry.
Zainab is meeting with, I don't know if, are you meeting with Larry or just contacted him? Okay. So she contacted him with email, but has already met him. No, if you want to visit with them again, I'm sure if you're available, but the way to catch him on short notice is to stop by his office and just say hello. And if he's in his office, he will almost always make time for you. If you stop by.
Yeah.
But if you try to reach him by email and short notice, you'll never get him.
Yeah. But be prepared, a meeting with Larry is a 2-hour meeting, even if you're asking just for the plan.
Yeah,
So,
he likes to talk. Yeah, so you sent him an email and he sent that he actually forwarded that on to us to ask. If we knew, did you see that?
yes, I
Okay.
did.
His question was, your proposal was mostly about small, like inexpensive weather stations. But then you were asking about eco-variants. He was wondering how much you were interested in eco-variants and how much just in weather stations. His thought was if it's really the small weather stations, probably we've done more with that than we have. But if you really want to learn the eco-variants method, definitely Larry. I mean, he's like a worldwide expert. He's one of the maybe top 10 people or something in the world on eco-variants.
You can see how much emphasis we're doing on the eco-variants, all things. Because for us, it's the measurement.
Yeah, that's all. There's been a number of them, and eco-variants has been the one that's lasted. But he would be, if you're interested in learning more about eco-variants, he would be willing to advise.
She's there. Yeah.
He does it, if you learn from Larry, he does the hard way, you'll learn everything.
Yes.
He doesn't use like easy software packages, it's all software he wrote. You go, but when he's done, he has a very high quality product. But for me, my eco-variants is I got a different type of eco-variants that has more user-friendly software. Because my science isn't an eco-variant, but my results will have more error. That's my trade-off, is that I don't. His science is that eco-variants, my it's not irrigation. So that kind of gives some thought.
What you want is clarity. What is your variance of IoT? He wants, because if it's a provider, yes. One know
Yeah, what you put part is eco-variants, then he's happy to, but if you want to come here and mostly focus on the IoT stuff, then his thought is published.
pricing instruments,
Yeah.
massive data logger, so IoT,
Yeah.
well,
So another option with your weather station, you could use your stations.
So I think this.
You could just compare to other twins and boxes like scientific grade weather. And that doesn't need to be. That could be something when we saw. We have them at a number. There's the one we visited at that first day. And now I lose track. Compare directly to those that station. Take particular ideal time. And you can assemble. I think there's enough equipment around. You can assemble your own stations.
And I know.
Again. And maybe we replicate, really thorough. There's, data covariance is really going to be if you're doing referencing, you don't compare that to eddy covariance. You be comparing to eddy covariance if you made a crop coefficient. You made a key model, an actual property.
Actually, but the weather station gives you the information.
And so there's a lot, either myself or Alfonso or even our colleague Sierra Young, because the Internet of Things is really, she does robotics and automation. A lot with like Raspberry Pi, You have one of those? Oh, okay. That's fine. I don't have one of mine. It's kind of expensive. Yeah. But Sierra's group does have a 3D printer.
He does. He's a printer. And he designed how to block the minimize concentration of helium. That can be studied. So, but that's IoT. That's not Larry. Larry is the size of
So that would be the thing. It's almost like you decide, I know that I have to my. Let's do the very Larry.
That can be
Yeah.
to run the operation process basically it's a goal and so
Ready to try. If you want to say
All right, let's continue the presentation, everybody.
Maha, when are you meeting with Yamin?
He not sent me an email today, so
Okay.
I am waiting
All right, okay.
for his response.
Okay.
If he not responds, I think we will go to water laboratory tomorrow. Yeah.
Yeah, we'll be at the water lab tomorrow. Okay. And I'm taking. Yeah, that's good. If he's in the lab, you're gonna have to wait till he has a break, because when you're in the lab, it's all.
I applied for the workshop.
Okay, good.
Workshop in
Okay, good.
Right. Opara.
Okay. So Hadir needs to go to the water lab to meet with Dave. David Rosemary. That's David Rosemary. At 11:30 is when he was available.
Okay.
And I thought that's important. So either myself or we'll see if Brian can take her.
Sure. Yeah, that's okay. All right. Let's continue our presentation. All right.
Okay. Okay. Sorry, did you see I took the Davis one off?
Yeah.
Well, I think their rain gauge is okay, but their wind sensor is.
Like it much. Like that's too complex to get it together.
Yeah, well, the problem with their anemometer is on a needle bearing. And in one season, it's worn out. So you can watch the data go like this over one season.
Yeah, we took.
So you can see it pretty obvious. So that's why I think this one for a similar price point is a much. I mean, but these guys build research grade things and Davis builds like high-end hobby stuff, right? Yeah, I mean, I think for research also, I have a research project that's using a Davis station, but that's because it's what was available. All right.
All right.
Thank you.
Yes. Let's continue with the presentation.
Okay.
Now we're moving to rain and weather data. From the satellite point of view, science, this was one of the first products that was developed from remote sensing. The science behind rainfall has been for decades, so more than 50 years. They have been studying how to estimate rainfall from radar, temperature, and optical data, or a combination of several of them. So products, there are plenty of products that can be accessible. GridMet is for the US, but the Persian rainfall product is, I think, is one that is worldwide and has demonstrated to be accurate. Now, in terms of weather data, the GLDAS provides this estimation of weather variables in a grid manner all over the planet. For the US, we have the NLDAS that is finer, has a finer resolution, but GLDAS covers the entire planet. And while I was checking these products, I realized that there is one specifically for Middle East and Asia. Is the FLDAS. That is focused on that part of the world.
Like this?
FLDAS. Yes. And that is oriented. The F is for famine.
Famine?
Yes. This is like a conjoint effort by, I think, the United Nations, several laboratories, but this is related with a farming program that exists.
What's the L? Is that land?
Is land. So for Egypt and the Middle East, a version of GLDAS is FLDAS. There is another product just specifically for that part of the world.
But the data with GLDAS is not good. It's not good.
The FLDAS?
GLDAS is not good. It's totally wrong.
Have you seen FLDAS?
I will try today.
This is another platform that I found while researching about this one.
FLDAS.
FLDAS, yes. That's it coming from Egypt, goes to Asia. It's a rectangle that starts in Egypt and goes towards Asia. So now on satellites, well, that might be the a piece of information that you can get if you don't have local weather stations. Whenever you can, double check the numbers. And this is because there are different levels of accuracy and it's related with time, with time range. A while ago, I did an experiment because I had this dream of doing water balance per pixel that didn't work. So where we had different products and we compared against local weather stations. We compared hourly, daily, weekly, monthly, and seasonal. Hourly and daily didn't agree. We had too much variability in the data. We had a one-to-one, but the differences could be large. But it's only when we reach monthly that the agreement between the products, that especially on rainfall, was really good. So, and annually or seasonally, the agreement was even better. So we have to be aware of this potential uncertainty in the data when working very short time intervals, like hourly or daily, because the models tend to be calibrated first seasonally, then monthly, and then we go toward the finer time scales.
Yeah, so one thing, two things. When we're talking about these large scale precipitation data sets, I was in a like a course one time, like a workshop thing. And the guy, it was about radar precipitation measurements. And his point was that when we use rain gauges, we miss 100% of the data because if you look at how many rain gauges we have and they're this big, and then how much land is around them, we basically miss everything. We're just measuring this. He liked radar a lot, but I always tell growers, I say, you know, you can use a weather station that's several miles away from your farm for a lot of management, but rainfall is one thing to measure locally, and so that's always a challenge. But even if it's for a study or for management and it's just a manually read rain gauge, that can be better than relying on something that's far away. It all depends on scale. The smaller the scale is, the more we really do need some kind of local measurement, and where we might get to the point where some sort of remote sensing product just doesn't work because of these scale issues. And normally when we're at the small scale, we're also interested in small time intervals. And so then we look more at like what we're going to do over here.
Yeah. So we show you the Atmos 41, this very compact instrument. How much was it?
For the one that has a built-in cell modem, it's $2,500 US. For one that is just the weather, and that you would hook up to your own data logger, is about 1,900 US.
So that price might be potentially affordable. So if whenever possible, use local measurements of weather and rainfall. Remote sensing, especially on these ones, the pixel size are 1 kilometer or 3 kilometers. So at farm scale is going to miss what is actually happening. So it's local measurements are always.
There's another one called Arable. Have you seen those ones? They're a group from Princeton University, a spin-off or whatever. They made this one. And I think their current iteration is pretty good. They started and then they field tested it and it needed more work. And I think they're currently probably pretty good. It's worth at least looking into. I think their price point's a little lower than this one, but some of their sensors are not conventional. So
this is how DayMed provides the data, and it provides daily, and from daily you can calculate any other time up to monthly or seasonal. And overall, they're pretty good. But at the parcel scale, which is a tiny dot there, it might miss. And this was the Atmos that we show you. Very compact. You just need a pole to put it at. What's the height you put it? 2 meters?
I normally put 2.5. The idea would be close to 3 meters, but that starts to get difficult. So about 2.5. It's a little more than 2.
Very simple, not cables, no wires. That's the best part of that sensor. Now, we haven't talked about this in the workshop, but we wanted to show you so you are aware. This is a brand new sensor. It's called the evapotranspiration sensor, and the company indicates that it can measure actual ET. This is this sensor. Probably you can explain better the theory behind this.
So this one, it uses the eddy covariance method, but it's simplified. Instead of doing the whole surface energy balance, we're looking only at the vapor, the water vapor flux. And so because of that, we have no way to test if we've missed something, if we accounted for all the energy. Another thing is we normally in eddy covariance, we take 3-dimensional wind speed at least 10 hertz. So 10 times per second, we're measuring the full vector component of wind speed, and we're looking at how when the wind is vertical, if it's got more water than when the wind that's moving up than wind that's moving down, then we have, if we look at if the air is kind of swirling around, if the water vapor is moving up, then air moving up will have more water than air coming down. And that's what the eddy covariance method is. But we use 3-dimensional wind speed, so we know which direction the wind was coming from that gave us that humidity, but also because sometimes it's very difficult to get the sensor perfectly plumb, perfectly up and down. It's always just a little off. And so we adjust that. We know that there should be a net of 0 vertical wind, because the atmosphere isn't like flying away, and it's also not just like crushing us to the ground. So on average, there should be 0 vertical wind. And so we can adjust the coordinate until we get that correctly. And so that takes care of our small errors in how we install the equipment. This one only does vertical wind speed, so it cannot do that, but it has a gas analyzer for water vapor. However, instead of costing like $50,000 US, this one is $5,500 US. So I just bought 2 of these, and we'll test them. We'll see. We'll stick them up to next to one of Larry Hipps's eddy covariance systems or something, and we'll see. If the data that they provided is accurate, then it's an additional plus or minus, I don't know, 5 or 10% from eddy covariance, but much less expensive. But it still requires the same installation. It has the same installation requirements that eddy covariance does. This sensor cannot be mounted near the ground. It has to be up 2 or 3 meters above the crop. It will see the land surface affecting it will be 100 times at least the height. So If it's 3 meters above the crop, we'll have 300 meters upwind that it is going to be affecting it. So it's still a large kind of scale measurement. It's not for small areas. But we're hopeful. This guy, George Burba, works for this company, Lycor. He's worked for them forever. And he's very good at the eddy covariance method. But he also works for the company that makes the equipment. So you have to, it's not independent.
But I might just mention, just to remind everybody, there is a second call for research proposals that are supposed to be coming out soon. And you are allowed to purchase equipment as part of those projects. So if there, this would be a good topic for research for the sector. Some of this equipment looks like it's useful to purchase. You can do that through I think the projects, the largest projects that are going to be funded the second round are about $1,000.
That's cool. Yeah, so something like this is very possible, or something like one of these.
The Atmos.
To get local weather data for a study or something. So.
All right, a new topic. Soil moisture. We have to go through the entire water balance, right? Okay. What do we know about soil moisture? Personally, it's going to be the last frontier of remote sensing. It's hard.
It's really hard to see things below any surface of remote sensing.
Extremely hard. People has tried to do it with machine learning, with radar, with a combination.
Microwave.
Microwave. They're trying thermal and microwaves, assimilation models, and it still refuses to work well. We have made progress though. 5 centimeter soil moisture data is possible. We can get it with local machine learning, with drone data, now with satellite data. That 5 centimeter, the top layer of the soil, we can do it now. It's possible. But the root plant is 2-3 meters. We need to figure out how to take or how to get more data, or how to figure out what sort of this process of the water movement from the root zone relates to the entire soil moisture conditions. And that is hard. We have a satellite. It's called the SMAP. That satellite was designed exclusively to monitor soil moisture. So it can do a 3-kilometer pixel, and it's a combination of radar and thermal and what is called a land assimilation model. And it's able to predict, or with certain level of accuracy, the root water amount. It's able to, but with some caveats. In some locations, it might miss it because it doesn't know the structure of the soil, and you might have a rocky layer at 1 meter, but the value that is approximating is saying I'm representing 2 or 3 meters. But this is the first effort towards that. Second, there was a recent publication, what is called the SMAP hydroblocks, where they use now data fusion between Landsat, Sentinel, high resolution satellite data with SMAP to bring down that information to 30 meters. But their caveat is only that they are able to do it only the 5 centimeter layer, the topsoil layer. Now, I in the past also wanted to give us a try. I was young and naive and I thought I could solve it. And machine learning can give you answers. One of it can predict we can provide information of the root zone. One of the limitations though is that the model is local, like it's calibrated for this area. The same model doesn't work in California. So it tends to be local. So to create a model that can predict that will have to be a machine learning that can use or incorporate data from different locations in the country. So that's a possibility. But this paper that I published a while ago shows the potential of using machine learning and remote sensing data along with direct soil moisture readings to create soil maps. So it is possible. Now, in the theory, I think in FAO 56 and additional publication, there are some empirical equations that relate what we call the fractional ET and the amount of water in the soil. And I think that's one of the Bastiansen equation behind IRRIWatch, because he provides soil moisture estimation, like spatial soil moisture estimations. So Catherine, one of my students,
It's a Dirk Reyes kind of thing, and they're probably associates. Do you know
yeah,
Dirk?
I think that's
His
it.
work.
Yeah.
Yeah.
So Catherine is testing these equations with the OpenET data to see, because we have some location where we have soil moisture sensors and we had an eddy covariance on top. So Catherine is going to demonstrate if these equations are holding true or we need to move into machine learning to figure out or to at least approximate soil moisture. Now,
So the machine learning is very powerful, but if you can come up with a simpler model that you know what the model is, there's value to that. Because machine learning, in the end, you don't know the model it came up with. You just know that it worked. Right? So.
And that's true. This paper that I did with machine learning, when was more than 10 years ago. That was, I think, my second paper of my PhD, and I was so excited. So now
you didn't have as much gray hair
yeah,
then.
I was black, really black. Yeah, but but then I decided I'm going to replicate that paper for my students in the remote sensing class. But now that I'm wiser and learned some other tricks, I think, what if I try to apply advanced linear regression theory on this? So I was able to replicate that paper that was done with machine learning with linear regression. And this is this and no, but this is the
So it
trick.
tells you what the machine figured out. Yeah.
So this is the trick. Maybe you have heard of this technique. It's called stepwise.
Stepwise regression.
Yes. Stepwise plus covariance analysis. Using these two techniques, like what I did is I generated over 50 vegetation indexes, everything that Google already allowed me to calculate for every location where I have a soil moisture. So I have one value of soil moisture and 50 potential predictors, 50 potential inputs. Then I use the covariance analysis to eliminate as many. And from that 50, I ended up with 17 that weren't correlated between them. On those 17s, I applied a stepwise regression And from those 17, only chose 5. So I have an equation with 5 variables that can generate the same soil moisture map that the machine learning do. So,
He's a machine.
so I have a code that demonstrates how I did that. I can share it with you. It's on GitHub. It's based on Google Engine and Python.
Oh, that's cool. That's a fun story.
So I need to take someone to the lab,
There.
ready to go. I think it's probably.
Thanks, Ryan.
Thank you. All right. Now, for soil's characteristics, going beyond soil or additionally to soil moisture, texture, structure, organic matter, there has been a series of machine learning applications that are worldwide. So most of that, where I could find most of them, those products, are in the Google Engine archive. So I leave you here the link so you can check what material has been on or what information regarding soil characteristics, like a water holding capacity, texture, organic matter. I think some of them try to do some estimation of nutrients too, an approximation of nutrients. So this is the link where you can find them all. On drones, we're supposedly to see better, right? Now we can see a tiny spot if it has too much vegetation, little vegetation. Still is a challenge. So here is another paper that looked to estimate the root soil moisture or root water content using UAV data, and it works. And it works, but again, the results of the capability of the model is local. It responds to this type of soil with these characteristics. Moving it to another place, it doesn't respond the same. Now, that's on the machine learning part. Now, there is a company called Terra.tech that has brought the radar, has developed a radar sensor that looks like a plate on the drone, like a large piece of cardboard that is sending microwave photos to the surface and retrieving it, and they have calibrated already the sensor to give you answers in soil moisture values. So this is, they were offering us the sensor for $25,000. So between 0 and 9, we haven't decided how we will come up with the money.
Yeah.
But it is happening. Like you see the theory of microwave and microwave. Did I mention that photons can penetrate half an object, half the wavelength? Did I mention that in the remote sensing part? No. So a photon that has a lot of energy. No, like a thermal, a microwave or thermal photon can penetrate half the wavelength. So the wavelengths of these photons are like 5 centimeters or 10 centimeters. They are not in nanometers or microns, they are in centimeters. The penetration is half the value. So if a wavelength of this sensor is 10 centimeters, it can penetrate 5 into the surface. So I think UC Davis is exploring this technology, but what will this provide is 1 meter pixel surface soil moisture readings. Now, that's on soil moisture. And yesterday we were with Kurt in the field and we saw soil mapping. And this was for soil characterization. He shared with us the results. And we saw that there was variability on that small area that we were able to map. So that type of sensor, the electromagnetic sensors and texture calibration can offer us this highly detailed map of soil zones that at the end will transform into management zones for precision ag. I think this information is the fundamental layer for any application towards precision agriculture. Getting to know what is the variation in characteristics of your soil.
On top of that, something we didn't really talk about was, well, we did a little bit, but about repeated measurements with this type of instrument. And there are groups who have used that to try to estimate changes in soil moisture by looking at what features of the map change in time. Maybe if you take a measurement this week and then next week and then next week, it's just kind of a lot of work to take a lot of images. This last one, cosmic ray probes, can be considered remote sensing because it's non-contact. Many of you will be familiar with the neutron method for measuring soil moisture, maybe using a neutron probe or a neutron gauge. And the idea is that if we emit neutrons, so normally we have some access tube and then a device that is emitting neutrons. Neutrons have an atomic mass equal to a proton. And so when they collide with the nucleus of hydrogen, which is atomic mass 1, and a neutron is atomic mass 1, then they both move. And that movement slows down the neutron. It takes a lot of energy out of the neutron. When a neutron collides with a nucleus that's larger than itself, it loses very little energy. It just bounces right off. And so it's sensitive to hydrogen because hydrogen is similar size to a neutron. And so what we do is we emit neutrons, high energy neutrons, and then we have a gas tube that is able to detect incoming slow neutrons. So a certain fraction of these neutrons will bounce around and will enter the sensor at a lower energy state. And so then the number of neutrons that come back to the sensor is directly proportional to the water content in the area around where it's measuring. And it's somewhere like maybe a diameter of 30 centimeters or so that it's sensitive to. With a cosmic ray probe, it's the same idea, but now we're relying on the sun as a source for neutrons. So we're always here at the land surface, we're getting neutrons coming in from space. And the same, like this neutron was, when those neutrons interact with water, they slow down. And so with this instrument, it doesn't have to be on the ground. Here's maybe the ground surface, and there's larger gas tubes because we have a much there are many fewer cosmic ray neutrons than when we're emitting neutrons from a local device. And so we use more gas tubes to get a larger signal, and it takes longer to make a measurement. But basically we have all of these neutrons zinging around off of water in the soil, water in the plants, water in the air. and a certain amount of them are coming back to the sensor. If we correct for the humidity in the air and for the vegetation, then this becomes sensitive to soil moisture. But at kind of a large scale, the scale of this sensor is maybe like 200 meters or something. We can't measure small areas with it because it's just relying on ambient neutrons zinging around. It's also like this. If we look at the land surface, the sensitivity is something like this. It's kind of exponential around the sensor. So you have to kind of look at what's the average depth. And it's also shallow, maybe in that 10 centimeter range or something like that. But it's another one here. This I just put here, it fits a scale between what the satellites do and what we can do with soil sensors. This is the company or a company that makes these. There was a lot of research on these maybe 10 years ago. It's kind of reduced. Some of the application is not. I think people thought we were going to get more out of them than we've been able to get. But it is one thing, mostly for hydrologists, less application in agriculture. But we've got hydrologists here, so it's one thing, and that upper soil moisture can be important in hydrologic modeling. So.
So this is an example of how HydroBlocks provides data, and it's quite detailed, the approximation they're doing. But again, this is a research application yet, not operational. They have an archive, and students in the remote sensing class have been able to contact the authors and extract or get data for their areas of interest. These, on the other side, are soil moisture maps using machine learning and UAV data. So depending for example, the center pivot was rotating in this image, and you can see the arm adding the water, increasing the immediate soil moisture of the spot. So it's still an area where more research is needed, or newer ideas, newer approaches, or maybe going to linear regression ideas.
Yeah.
But we need more, because this is the hardest, but it's very fundamental. The soil is our deposit of water, and understanding how much we have in the tank will allow us to decide when to irrigate, next week or today. And if we're reaching critical amount of water, that might reduce the production or the yield that we will get at the end.
One thing I'll point out is it's interesting because in a lot of conventional water balance research, change in soil water content has been what we're able to get. And we have a really hard time getting ET. With remote sensing, we've kind of flipped that problem around. We're much better at getting ET because that's something that happens at the land surface, and remote sensing has a hard time seeing underground. Maybe we need to use like FM radio waves or something.
Yeah.
AM, it can travel through mountains.
Hey, groundwater or lower or higher water table. Satellite, in the satellite realm, there is a satellite designed for groundwater, called GRACE. And the follow-up satellite, because that satellite already fulfilled its life cycle, now is the new satellite is called GRACE FO. It follow on. So I leave you here the website. what it does, and this is a very clever technique that NASA scientists is not remote sensing, or is kind of remote sensing, but it has nothing to do with photons, not microwave, nor radar, nor optical. Is gravitational pull. As let's say, as a satellite circles Earth, when it passed over Mount Everest, the gravity is slightly higher at the Everest than when the satellite is at the ocean. And this has to do due to the mass density. So, in locations with large aquifers where water extraction is quite dramatic, that pull it can be felt by the satellite. So what they developed is this satellite is a pair of satellites that are always measuring the distance between the satellites. And when the first satellite goes over, let's say, California, which has been always has making very extensive use of their groundwater resources. So every year the satellite feels a slightly less pull. And that pull causes that the distance between the two satellites increases or decreases. So they relate this measurement done by lasers, which is photons, which is remote sensing, with the gravitational pull of Earth. So this technique has been used to monitor ice melting or tracking of glacier changes, also to monitor changes in large aquifers. In this case, the Amazon basin, California, and India are the poster childs of the application of the GRACE technology. I haven't seen published data for Egypt, but it will be interesting to play with it because all the data is in Google Earth Engine. So you can extract a time series of the variation of the aquifers for, let's say, the delta, and see how that how the aquifer is behaving on those regions. On drones don't have that technology. But what they collect is the complementary information. They will be able to describe the vegetation, the topography that can describe some, let's say, artesian wells or locations where water will be contained towards the aquifer. So the drones will provide you that very detailed information about what factors from the surface are affecting the aquifer.
And so if we're talking, so when we talk about water balances, there's kind of the different scales. We have our basin scale water balance. We have a field scale water balance, or an irrigation system wide, water balance. We talked about this one earlier today, the inflow of groundwater, shallow groundwater into the root zone by capillary action. This one, we often just rely on, if this is really important, we rely on it being the residual of the other inflow. So if we start to see ET is greater than our known inputs, that's usually how we identify that this is happening. It's difficult to measure. We can model it, and we'll talk about modeling for deep percolation, but it's the same physics for other things.
Yeah. So let's see the poster child. This is the GRACE satellite information as the aquifer of California gets depleted over time. So red means more depletion, and the GRACE satellite has been fundamental to understand what was the level of impact of agriculture on the groundwater conditions. So a similar figure exists for India. And the other location is the Amazon basin. So NASA created these maps, and in Google Earth Engine, you can like click on any point or define a location, and you can extract the total records of the satellite for that location. So you can see the periods where the aquifer is recharging, where the aquifer is declining. So you can see over the years the overall trend of how the aquifer is either going down or efforts to restore the aquifer or natural causes that are causing that the aquifer is going up. Okay. Not everybody records how much or when they irrigate. That's a problem. Yeah, that's a challenge because if we're doing water balance, we need that information. So this is something that I came across a couple of years ago when I was developing an online course on irrigation and remote sensing. Is this model called soil moisture to rain. What it does, it uses the remote sensing information to infer the occurrence and the amount of any water source input, in this case, rainfall or irrigation. This is done initially with SMAP products using that 3 kilometer pixel, but the team is working, this is a team in Italy, is working to make it closer to Landsat. So this is something that it works to keep track of it because there might be fields and areas where we don't have information about when was irrigated, but soil moisture data is available or present, then can be used on that. So
That's kind of a universal. There's never enough information about how much water was applied
Mm.
in there. I mean, we do in our research plots or something, but in producer fields, it's not very common.
on drones, well, this research, because drones are not like frequently flying, we don't have like every week or every 3 days flying. Haven't seen anything related to these two concepts, but what we need to do in our research is to get the measurements, to get the direct measurements, and when it's flood irrigation, that's where it gets tricky because we can have multiple inlets of water and monitoring how much water is passing through and keeping clean records about that. It's not that every producer does. But when it's pressurized systems, solutions to mount like this sensor that you put on during our field day.
Yeah, so then we get to this one, which is, this is like the ideal. But what we're talking about is how to get, how do we get that information if we don't have those direct measurements?
Yeah. But promoting measurement or tracking measurement of irrigation, it's important. Because one is our baseline. If we know how much ET is happening, but we don't know how much water is going in, we don't have an idea if that water management is efficient or not. So measuring will give us an idea to say the resources are being used in an optimal way versus there are opportunities to enhance the application or the use of water in agriculture.
So I put this one in coupled with uniformity data, you know, to tie it back to the why were we walking through the mud. But it really is helpful to have both, to have an idea on how that water is distributed across a field, across an entire canal system. And this, the uniformity part, is something that we can do something about with remote sensing.
Yes.
Alfonso talked about that, right?
Remember when we found a center pivot, which NDVI was higher at the center and lower towards the edge, and it was everywhere, all around the center pivot. So that is telling us that it's not soil. If it's showing a circular pattern,
Soil doesn't usually form that way.
so is the water. So it's telling us already that it's losing pressure. It might be-
Probably.
It's losing pressure towards the end. So that center pivot is worth doing the test that you conducted with the gauges and the spreadsheet that you had.
So I was asked once to give a presentation at a regional conference. So some of the states a little bit east of us, Colorado, Kansas, Nebraska, they're a little more humid than here, but a lot of their western side is a lot like Utah. And they have a conference every year that's not really for academic people. It's really geared towards water users, irrigation companies, farmers. And so it's kind of a neat little place, but I was asked to give a presentation on using remote sensing to assess irrigation performance or uniformity or something. And I found a paper where somebody had done that with Landsat for center pivots. It's a little tricky. I have some ideas on how it could be improved. It would be kind of fun, but right now that's untested. So wait and see. No, I don't know. But a lot of it was just visual. You can see it. Quantifying it's trickier, but a lot of times you can see it. You especially with sprinkler irrigation, you can see it. But whenever you see problems that match the geometry of how you irrigate, we saw that in the center pivot. If you have a field and it's irrigated with a different kind of sprinkler, like in a grid or something, but you see anything that follows what a sprinkler does, this is a uniformity problem, right? And a sprinkler, if a sprinkler is properly pressurized, then if we draw a little graph away from the sprinkler, and here is depth and here is distance r, like radius, properly pressurized sprinklers should have close to a triangular shape for most sprinklers. And that's not always the case, but that's often how they're designed. If it goes something like this, this is probably too low of pressure. All the water's falling in kind of one area. If it goes like this, it's too high. The water's all breaking up at that sprinkler and it just isn't traveling far. Surface irrigation, we start to see things like streaks. Or, if you have a field and the water's flowing down, if it's poorly uniform, it'll go more rapidly in some areas than others. Or maybe we'll see high points that the water is flowing around. We can kind of see how that would relate to the irrigation system. Alfonso talked about drip systems and how if you fly them with thermal, you can see large cool areas that indicate that you've got a leak that may be hard to see from the ground, but we can see in an aerial image.
Mm.
So,
So
thoughts?
it can help especially thermal data can give you feedback from UAV, but it's mostly how is the system operated. I mean, do we have issues on the of pressure or breakage lines or areas that are less irrigated, so they will be hotter than the rest of them. This is a picture that I got from this model soil moisture to rain, where is the green lines are the observation data, the true values of rainfall, and the red line is the model itself, as the soil moisture to rain. It can follow the pattern, it can match some of the peaks, also it misses some of the values of the peaks, but overall it follows the trend of rainfall.
Who's a hydrologist here? If this was a hydrograph, a modeled hydrograph, you'd feel like a superhero if you got that kind of match though, right? It's never that good in hydrology. Anyway.
But yeah, that's so it's a very promising technique. So keep an eye on it. It will be moving to a finer and finer scales. Oh,
What was that? Oh.
runoff and
The hard one.
interpolation. We don't even think about measuring those. We don't have even techniques to track these values. So,
All right, yeah, well, why don't we take a second and talk about that?
all right.
So this one, runoff, we measure at a basin scale, maybe on a river gauge or something. But small scale, how do we measure that? If we have a field, here's our plants, and we know that during irrigation or during rain, a certain amount runs off. How do you even measure that?
Measure the runoff.
Yeah. Thoughts? Anybody done it?
Sometimes we measure the charge at the end of the field, how
Mhm.
amount of water goes to the drain.
Yeah, there's a drain.
Yeah, we have many things to measure it.
Yeah, usually it involves putting some kind of small plume or something in the field or in a drain. You know, maybe there's a drain at the end, and so we can put a weir or a flume in the drain. Some people put these little, if we're looking straight down, they'll put a little device, just a little metal, device that captures water and then drains it into something in the ground. You know, if they're trying to get the runoff here before it gets to the end of the field. But it's not a simple process. So there's a reason why we usually model it, because it's a lot of work. I won't talk about deep percolation because we'll talk about it in a minute. But so
We model. So there are two approaches for satellites and for drones. And I don't know if you are familiar with Warp Hydro. This is a numerical model that looks to integrate climate surface data to model all the components of the water balance. Is done for like to track the water balance component in basins. It works really well and it keeps evolving every year and is part for the US is part of the national water model. This is the engine or the algorithm behind this to track, for example, potential flood issues, drought, or impact of natural vegetation. This is what is done with satellites. This is a large scale, basic scale modeling. Now, on more local or finer scale, there are these numerical water balance models that I haven't had the opportunity to use them, but we have people here at Utah State that work with this. Scott Jones is one of them. That it will take a lot of information about the soil characteristics, about it, the changes in structure, texture, potential carbon layers, and we'll look or we'll try to model applying Darcy and Bedouin theory. We look to model the different components of the water balance, including runoff and deep percolation and capillary rise or shallow groundwater contribution. So this is what does this. On drones, similarly, this Hydros 1D, 2D can be used with information about the drones that could provide either ET data, it could provide vegetation conditions data like NDVI or changes of NDVI to model that. So that's how far these two components can be approximated for a single field. Now imagine having 100 or 1,000 fields. So that's where still we are at the very local scale or a very large scale, but nothing yet in between.
Yeah. And a lot of our hydrologic models are really meant for larger scale hydrology and don't work at the field level, but we do have some things we use. We do sometimes use some of our traditional infiltration models like Green Amped. Also, a lot of times in my research, I use the Soil Conservation Service method. Do you use that at all in your research or in your teaching or anything? The SCS method?
Yeah.
And everybody says, it's kind of a miracle that it works. It shouldn't work, but it kind of gives good results.
Yeah.
So we keep using it. It's simple. I use this one, but it's usually just to say, yes, we know that there's some runoff, but we have a small amount of precipitation during the growing season. And so it's okay if our error is kind of large because the value is small. For building off of what Alfonso was talking about with Hydrus, which is an N-saturated flow model. This isn't remote sensing, but we showed you some matrix potential sensors, and we can use those types of measurements and this type of modeling to get at these two down here. But it's not remote. It's still not where it would be cool to get. The problem is, it's like everything below this shallow soil layer is too deep for remote sensing to see. And so we're not there yet. So a lot of times we're using a soil water balance method. If you're familiar with FAL 56, in that method, we're using a water balance to kind of simultaneously adjust ET and estimate deep percolation. We're almost always neglecting capillary rise. But we're sitting there using a soil water balance and trying to come up with a reasonable estimate for this one and for ET at the same time.
especially if you have a shallow aquifer, which happens on some locations here in the valley.
Yeah, you've had it, and you and Neil did that research out in Colorado
Yes.
or in eastern Utah or whatever it was,
yes.
Wyoming, something.
And we were tracking ET on these farms that the farmer stopped irrigating. And the plant was still growing, the grass was still growing. So the plant, the water was shallow, and then when we did it, like topography profiles, we figured out that the river was high enough that the water table was like a meter and a half away. So when irrigation stopped, the plant just developed more roots and keep growing. So that was a big blow on this study that we're doing. Can we track it? Can we track voluntary following conditions on farmers? And the answer is it depends.
So it's important because in that condition, this is on the Colorado River. And so the idea was that people could stop irrigating pasture, and then that water would then be conserved and be available for downstream uses. But if the plant's still transpiring, it's still depleting water out of the hydrologic basin. It didn't matter if it was irrigated or not. It was the same water loss from the basin.
But it's depend about the depths of the groundwater. How much?
Yeah. So most of these pasture land were nearby the river. So just doing this cut on the topography, you will see that the height of the water in the river allowed for a shallow water table all across the river. So so water was still being depleted, but the farmers were being paid for following. So it was like an issue because the farmer is not physically putting the water in the canal and putting it in the field, but the plant is still using water that is supposed not to. So they were expecting that ET will go down to zero, but ET was not zero.
But also it can be happen at the last stage or the middle stage of the plant growth time. Not at the first stage, because the root depths at the first stage it's very, very shallow.
In this case, it was because this is pasture, grass, and this is overseason.
Yeah, it's perennial. So yeah, so in the lower Colorado River Basin, they have a lot of these programs, and they're able to do that. They're able to just kill the crop.
Yeah.
And then they just make sure there's no weeds, because sometimes they can get a lot of weeds, and the weeds, they go down and find the water. We have other places where this happens. We have people that irrigate here, and then that builds the water table up somewhere else. And so if this person stops irrigating, they're still ET. And it still reduces the flow, the return flow back to the river or something. And that's a big challenge. It's a big challenge in Utah right now, because people are very interested in getting more water to the Great Salt Lake. But many of the activities that they're doing are not reducing ET. They're lining canals. They're sometimes changing to irrigation systems that have more loss, like sprinklers. And it's really nice, and it can be very beneficial to the farmer, but it just doesn't change what's going to the lake. And so these kinds of things, being able to track this movement of water at the field level even, is really instructive to people, because they're not realizing that I made this change, And all they're changing is the path of the water. They're not changing the actual amount of water that goes to the lake or that goes to ET. They're just changing how the water gets there. And so that's a major value of doing water balances at the field scale, at the irrigation system scale, and then matching that up with what our hydrologists do at the basin scale. It's the kind of things hydrologists think of all the time, but politicians don't. So.
This here in the US, there is a major effort on training scientists to use the warm hydro model. USU and our director, David Terbotton, is a major user of this. He does a lot of research on this area for basins, and USU actively participates on these efforts. And this one was, let me see, what was this? Oh, Hydrus. This is information coming from Hydrus over time. So it will model moisture, it can model temperature or expected temperatures given the conditions of the farm. Probably this is the most important slide. Yield and its relationship with water. And yield has been in the minds of, is in the minds of any producer. Right? Would I get the same, better, lower? Should I buy insurance? Should I change crops? Should I? At the end, at the beginning of the season, they have to decide and they stick with the consequences. So there is a lot of going on around running a farm business. It is the water, it is the fertilizer, it's all the inputs, it's the equipment, the personnel, it's the market, it's the price, it's the timing. So water is, for the farmer's mind, is one component of many.
And it's often an inexpensive component compared to nitrogen,
Yes.
for example.
And the energy.
Yeah, energy.
And the energy.
It's what's it? Pesticides. Pesticides are really expensive, right?
Mhm.
And so sometimes, so in a location where energy is expensive,
Mhm.
and pumping is required, then water becomes expensive.
Yes.
But if energy is only required for things like harvest and planting and tillage, so for here in Utah, that energy is expensive because it's diesel.
Mhm.
But electricity is inexpensive, and so pumping energy, that usually doesn't change whether or not a farm is profitable.
Mhm.
And so sometimes the water, it's not the value of the water, it's really the value of the water on yield.
Yeah.
That is going to change whether somebody is willing to do something or not. If you can demonstrate, look, that field, that pivot, right, that looked like this, and there was a lot of green here and not so much here and not so much here. You could say, look, you want that whole thing green, make some adjustments to your center pivot. Sorry, I'm drawing too low below this. And that makes a huge impact on yield. Now somebody's going to take the time and go do it. But if you'd say, oh, it'll save you, 1,000 meter cube of water, then maybe that's not very expensive.
So efforts to relate how we apply water and the resulting harvest has been done for decades and is one of the first things to do research on. And still is in research stage, especially with remote sensing data. And I put an asterisk on that phrasing because on my knowledge, there are two approaches. One is a sort of numerical modeling that will look into the physiological and phenological parameters of the crop, the growing stages and when reach maturity, different type of stresses that happen to the plant and how they are related with, let's say, water content and the opportunistic application of water. Those models exist. One of them I had the opportunity to work is the FAO aquacrop model.
Who's used aquacrop here? So aquacrop is wonderful because if you're a water person, aquacrop's the best, right? Because we're really only worried about water. If you want to include the other things, there are a lot of other models, but they're all more complicated.
Aquacrop is not a complete model. It won't include nutrient requirement or doesn't try to track nutrient levels. It numerically represent the theory developed in these EPGL functions that published by FAO, plus a soil water balance model that will internally also calculate evapotranspiration using crop indexes from FAO 56. In that regard, is a tool that, as long as we have weather data and information about the soil characteristics, it can give you an estimate of, let's say, what happens if I have an alfalfa field, I have no water this year. When the growing of my crop will stop just by using rainfall, and what will happen for the rest of the season? It gives me a rough idea what will happen with the crop if I go just rely on rainfall. Or what happens if only have half of my share of water? I can input that information into aquacrop and see what happened with the expected yield. Like if I have alfalfa, instead of doing 3 cuts, I might get just 1 or 1.5. On that regard, aquacrop allow us to be very flexible on that, on how we create scenarios behind it. So this is something we use this last semester. We use for some of the students that came from Egypt. We showed them how to tune up aquacrop, how to get the local data and the soil parameters and evaluate the scenarios. Now, one thing that aquacrop doesn't do is aquacrop doesn't ingest any, aquacrop internally calculate ET. It's decided to do its own calculations. So there is an opportunity on aquacrop to use the satellite or drone ET data, right? Because this is using crop coefficients. But we can provide a more, let's say, local information, spatial information using satellite data, drone data to aquacrop to affect the resulting yield conditions. So that's something that I have a colleague in Spain that is trying to do that. Is trying to do a spatial aquacrop.
Who's that?
Her name is Roxana Porras. She's in Spain. And aquacrop exists in 2 versions, like the software itself and the the Python version. So the Python version can accept spatial data, and she's studying how to add spatial information to that option. So instead of evaluating one field with the software, you evaluate several of them. So that is AquaCrop. And for me, it was a very didactic teaching tool to model scenarios. What happened if water shortage, or just irrigating with rainfall, or changing the soil structure, or same soil, southern in the US, going northern in the US, changing the weather parameter, what happened to yield? So those scenarios are very easy to implement in this piece of software. That's for AquaCrop. Now, I mentioned that I said this is a research stage, and that's for AquaCrop. Commodity trading, or the buy and sell of grains and fruits and such, is happening every day. And the prices have been decided 6 months ago, not today. How? It was done. It is done with remote sensing. The US Department of Agriculture uses the archive of Landsat across the planet. And he's tracking how much grain is produced in Ukraine, how much cereals are produced in Russia, how much corn and soybean is being produced or is growing in the US, and he is comparing it with historical average. And that information goes to this commodity market where you can do future trading. So these companies will bet on the price, and they will buy future commodities. And that's where, let's say, the price of the bread of today was influenced by the tracking by satellite of vegetation indexes and map classification and all the remote sensing stuff to say this year the production will be 10% lower than last, or will be 10% higher. When the Ukraine-Russia happened, those models were updated and all the prices just went up. 2 months ago, a pack of eggs was $2. Then, for no reason at all, 2 weeks ago, it went to $4. And then again, it went to $2. Something happened in that period that influenced the price of grain that is fed to the birds, and then the price went up. So the prices are not just random. There is a whole industry behind this yield monitoring and remote sensing. So what do they use? They use empirical, like linear formulas, machine learning formulas to do this forecasting. I'm in month number 2 of soybean, but do I have enough information to forecast the end of the season, the harvest? So where a lot of money and resources are going is on this part.
So we had a colleague, Isidro Campos, and he made a model for maize and for soybean, but I think for both anyway. But it was a crop coefficient model. So basically what we've been saying, the ET fraction, but it's in his version, it's based on Savi. And for maize, it looks like this. Very much like a shark fin. And so he fits this, and if you integrate this maybe days. If you integrate this curve, you get a really good estimate of yield. But what's important to know is if there's any water stress. If there's any water stress, it reduces. You have to reduce it. So you have to run a water balance model and determine if there's water stress. And if there is, you reduce just like you would in like FAO 56 or something. But then the integration of this area here makes a very good estimate of biomass. And that's really what we're good at estimating with remote sensing is biomass. So this would give biomass production, and then they relate it to grain production using a harvest index. But that's been a very effective method, and it's basically this. And aquacrop is basically doing the same thing, right?
So this is the website for Aquacrop. This is the handbook, and also give you access to the software itself. And this is the Python version of Aquacrop that allows you to do a spatial analysis using the functions of Aquacrop, but in multiple fields at the same time. Okay, we're close to the end of this presentation. Now, the question is, can we put all these pieces of information coming from different satellites, models, accuracies into one package and solve water balance? That's a hard question because every component, the SMAP soil moisture comes at 3 kilometer pixel, Landsat at 30 meters, rainfall at 1 kilometer. So how we make sense of all of this? So then there's going to be effects or impact of when is available the data itself. Like I might have daily data, daily rainfall data, but it happens or it's not available today, it will be available in a month. So I cannot run my water balance today. Or is the frequency, is it estimated daily, hourly, weekly, monthly, or seasonal? Resolution, how often, what's the pixel size, and accuracy. As the example of rainfall is more accurate of monthly estimates than weekly or daily estimates. Now, NASA, and this is mostly for hydrology, they have done a really nice work, put all the pieces together for phases. And this is called the NASA LEAS project. This also in NASA ARCET, in that website for education, there are workshops about how to use this system. But what it does, it integrates these different products coming from remote sensing to do this integrated water balance on a specific area, basic or sub-basic. Now, on a farm or let's say a more smaller scale, there is still work to do. And there are opportunities to advance, try to build a framework for all of them, improve or develop new techniques on improving, for example, soil moisture estimation or stress estimation. There are some publications that are looking to do this water balance at field scale, doing a mix of remote sensing and ground measurements. And there is interest to do that, but these models are always ending on the researcher realm yet. So we're still waiting for that application or that approach that can help us to integrate the different water balance component and supplement with local measurement what cannot be done with remote sensing. And this final
That's
measure,
what I added. Alfonso's like, "Oh, what's going on here? No. The idea here is, so we have our different ways of estimating things. Often we don't. Often we're estimating most parts of the soil water balance and leaving something for residual. But if we can get to where we're estimating every part, then we can start to look and see if we're getting closure. Are we actually accounting for all of that water? And how far are we off? Because that, if we're off by maybe 300 millimeters a year of water, where did that water go? That's a lot of water. We should be able to do better than that. But, you know, if we're only off by 20 millimeters of water, that's probably acceptable. It's hard to track that much water. So kind of in the end, the idea is to get to a place where we can actually look at closure. We've come up with an estimate of everything that doesn't force closure. We're not relying on the water balance to compute something. We're estimating each component of the water balance, and we can look at closure. That's kind of the goal.
we need to have flow.
That's the target. We're usually not there in our methods, but that's the goal.
Other considerations. We have all this data, let's say we have all the components of the water balance, the ground measurements that we need. Practical consideration is when the results will arrive to the producer or the person that needs to make decisions. That is going to be a always moving target. Satellite, for example, Landsat data level 0 is available within 2 hours of the satellite overhead. Level 1 is by the end of the day. Level 2, 2 days later, or 2 days or longer. So it's not real time. Okay, so if let's say I'm tracking a massive wildfire and I need level 2 data, I'm off. I need the data today, right? So then it's going how often the data or the results to make the decision are going to be available. It's going to depend on the complexity of the analysis. So the more layers of information we have, each of them require their own time to be generated, is going to take long. And our goal is to reduce that goal. To give you an idea, for drones, remember we went to the field, we flew the cornfield, right? We didn't flew the alfalfa, but you did the example on alfalfa. Why? It's because processing the data of the drone will take us 1 to 2 days. Okay. So for us, that's something that we can address with some engineering, some cleverness, and some luck. If we believe we can do it, we are starting up. We started last year a project where we're going to put a very small computer next to the drone camera. And as the drone is taking pictures, this small computer will be calculating the reflectance of it, will be putting together the images, and we already have a very early prototype of that. So it's possible to reduce that 2-day waiting to 30 minutes or real-time up. So our idea is, okay, it's 2 days for processing the data, another day for ET, or an additional hours for ET. So we say, okay, what if we take our knowledge of ET, we simplify it in a way that It's faster to run, doesn't reach too much accuracy, and can be run inside this tiny computer. So we want to bypass 2.5 days to 30 minutes. We started with the first prototype that takes the individual pictures and create the map in the drone. And we were successful. We have an early prototype. Then, so now our task is, okay, DSEP, how we simplify DSEP so it can run 1 picture per second. Has to be that fast. Every picture that the drone takes, it will be doing the energy balance calculation. How we simplify enough, but without losing too much accuracy. Because one of the things about compressing the steps, we have to bypass some processes that might take too long or replace them with another approximation. So that's what we want to.
You search a way to take a quick decision to be applicable for the field or for what? Why do you want to minimize the processing time?
Because when you are in the field, right? Again, the producer, the manager is a busy person. He has many things in his mind. He needs to know what's happening in the field. One question that they ask me when I go with the drone, could I look at the thermal data to see if my drip lines are working okay? It's just as simple as that.
Hmm.
And I have just pictures, I don't have a map. So this effort is to respond to that need for immediate information. They need to decide while you are there while you're there, where they need to send the workers to repair.
I mean that.
Okay, or so there is a need for urgency of the data. So on the drone area, that's our vision. Along with the crop water stress, this is the other area that we want. We want to put this in a tiny computer and get the ET map when the drone lands. It won't be perfect, but we want to get as close as the normal run will take. So that's one thing. But now that prototype, that might be very expensive and only large producing companies might be able to afford. What about the small farmers? What about the other producers? That's a difficult question. And it will respond to the socioeconomic characteristics of that region. For example, here in the valley, I don't think anybody uses Landsat to track their crops. Or they might be initially looking at OpenET, but it's not common. But in the Amazon, tribes are using satellite data to track almost in real time deforestation. So it's a matter of where the priorities are and the need or the access to the data. Because for these tribes, the entire package from satellite data all the way to a tablet that can be charged with solar panel and thus you don't have to enter input, just click the buttons and give you information, has already been done. So solutions like that might be needed to be generated for individual smaller farmers. Now, that takes not only understanding or it will understanding of the priorities or the needs of these farmers, but also how to bring that data in a way that is understandable and usable to them. And that requires a different way of creativity. It's not pixels, it's not GIS, it's how you transmit now that information to this community in a way that they understand. So the second part, how all of this can be integrated into water management, it will depend again on the expertise of the team receiving the data or the people receiving the data. In these large farming companies in California, they have their GIS laboratories. They have PhDs, computer science people that they use or look at Python code, and they can generate parcelized information, summarize tables and such, and inform that information to field managers. So for now, Landsat is widely used. Not even in California, drones for mapping are heavily used. Why? Because of this time delay to get the data and the additional time to process the data. While Landsat is more reliable, covers more area, and you get enough pixels to get the average of the field. So the main approach is that satellites will give you that average value for the field, but drones, as their cost and applications become more effective, they will be proposed for precision ag towards yield, towards improving low production areas or minimizing costly input applications. And this is still research. This is an active area here, many universities where everybody tries to present an idea that can work. What more is very worthy is an incomplete list. Okay? What you saw is just our partial knowledge on these topics, and there are more. There are topics on robotics, proximals, IoT, Scarlett, there is one that is edge computing that are happening, and later or nowadays might be already integrating with water balance and information happening there. So, but the good thing is that the fundamental science on water balance and especially ET has been already developed. We can make use of that. Yeah, this workshop you had the opportunity to manipulate the data and obtain results. So we're good on that part. There are many things we never mentioned: water stress conditions, flowering, nutrient estimation, disease detection, that influence water management, and remote sensing can contribute to that. Now, these robotics and proximal sensors, we didn't talk about advances in data collection irrigation systems, but that means there are many opportunities for research and continue these efforts in Egypt and here. And that's it.
It's a very important presentation. Please send us now. Now to us.
Right now.
Yeah, right now.
This was called alarm. Alarm.
For tomorrow?
Today.
Today? No, not today.
Yes.
Yeah, alarms for us is to.
All right. All right. Oh, you're some of you are fasting today, right? I see. All right. Should we take a break now?
Yeah, I think.
Yes. With the service.
we're,
The next